Hello, I'm David. I'm one of the lecturers at the Maths Learning Centre at the University of Adelaide, and this is the Rough and Ready lecture about linear equations. Okay. Right. Well, this topic is about solving systems of linear equations, and it would be a good idea to have to know what linear equations are and what the point is. And the point is it's actually about points in 2D and 3D. So just let me get you up to speed on that. In two dimensions, we write an xy coordinates, and then every point lines up with spots on the axes, and for example 2, 3 would be this point which lines up with 2 on the x-axis and 3 on the y-axis, and -1, -2 would be this point which lines up with -1 on the x-axis and -2 on the y-axis, and so on, and there'd be 0, 0 as well just here, which lines up with 0 on both, and this would be 1, 2, 3, 4, 5, 0, and every point has coordinates. And in 3D, well, we have to do this, it's a bit harder to do, but I can get something like this, a box, and I can say this is my x-axis, and this is my y-axis, and this is my z-axis, and just let me draw some labels on those axes. The box is supposed to go on forever, by the way. But if I had like 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6, and then 1, 2, 3, 4, 5, 6 up here, then the point 2, 3, 0 would be at this point. And then 2, 3, 1 would be here. 2, 3, 2 would be here. If I wanted -2, 1, 1, then I would go to -2 on the x-axis, 1 on the y-axis, and then 1 on the z-axis. And if I wanted to go, 4, 4, 7, 4, 5, 7, 1, 2, 3, 4, 5, 1, 2, 3, sorry, 1, 2, 3, 4, 1, 2, 3, 4, 5, and then 7 would be 1, 2, 3, 4, 5, 6, 7, about there. And if I wanted 4, 5, -7, that would be under the table because I have to go down. That's the idea. And normally you would draw it like this. It's in 2D, this is in 3D. You would have an x and a y, and you imagine the y the xy plane that you see here is fallen down backwards, and then there's a z plane up. And you might say, 1, 2, 1, 2, 3. That'd be 2, 3, like 5 here. Something like that. Okay, so that's coordinate geometry. And one way of dealing with coordinate geometry in 2D and 3D is to use vectors to get a handle on how to move around in 2D and 3D. And you can talk about angles and parallelism and parallel vectors and lengths and that sort of thing. Another way is to write equations to describe sets of points. So what you can do is you can create some sort of formula, and you can find all of the points where that formula comes out to a certain answer. I'm just going to jump over to the computer to do this now. So I might have a formula 2x plus 3y equals something, and I might move this point around and see what it does. Just let me do something. Right, just made it bigger. So what I might do is move this point around and see that the answer comes out to different things. So here at 4, get exactly on the point 4, 2, I'm not sure. It's a bit hard to get it exactly on the point I want. Here at the point 4, 2, it looks like it comes out to about 14. There it is. about 14 at that spot, but if I move it off a little bit, it'll be different. And that's because if I go 2 times the x coordinate, which is 4, so 2 times 4 is 8, and then 3 times the y coordinate, which is 2, so that's 6, 8 plus 6 is 14. Whereas here at 0, 0, it comes out to 0. Here at 1, 1, it comes out to 2 plus 3, which is 5, and various different things. So it'd be a different answer at every point. So if I wanted it to come out to 9, then I would need to try and find out where it comes out to 9. So let's see, 11, 10, 9.6, 9, oh. There it was. Comes out to 9 somewhere in here, right? Found one. Oh, missed it. And then over here it's sort of 15, 14, 12, 9.6. Comes out to 9 about there. And over here it's 14, 13, 12, 11, 10. Comes out to 9 about, somewhere in there. Coming down, it's like 0, 1, 2, 3, 4, 5, 6, 7, 8. Comes out to 9 somewhere in there. And I can figure out that there's all these points which seem to be along here where it comes out to be exactly 9. And in fact, if I turn on this, Desmos is good at just basically calculating for every point whether it comes out to 9 or not, and colouring in the ones where it comes out to 9. So all of these points will form a straight line. And it turns out that if you go number x plus or minus, plus or minus number x plus or minus number y equals number, then it will always form a straight line equation. And these are called linear equations. It is possible to draw all sorts of wicked other strange lines. So strange things. You can put whatever equation you want. Oh, that's not what I want. X squared minus yx. Turn that one off. And this one produces this weird ass thing, and I could change it to something and it turns into something like that. All sorts of strange things that could go on. And what the computer's doing is it's essentially checking every point and seeing which ones come out to the answer that I just said and which ones don't. And if I change what that answer is, it will slightly change what the function looks like. Okay. But we're not going to investigate those ones. We're just going to investigate linear equations. Okay. Let me just write that down. In 2D is of this form. AX plus BY equals C for some fixed numbers A, B, and C. And a linear equation in 3D is of this form, AX plus BY plus CZ equals D for some fixed numbers A, B, C, D. Okay, so that's what a linear equation looks like, and it turns out that if you collect together all of the points whose coordinates satisfy a linear equation in 2D, it always forms a straight line. Sorry, just sharpening my pencil. So, in 2D, points whose coordinates satisfy a linear equation form a straight line. Okay, that's what happens in 2D. And you can see this straight line here on the graph. If I change this number to, say, 10, then the graph moves a little. Let's change it to 15, 20, 30, 60. I mean, it is still there. It's not just this bit here. Technically, the line goes on forever and ever. Just zooming out and now zoom back in. I can't see it in this picture, but I can see it there. And I could even make it 0, and I could even make it -7 or -20. And what that does when I change that number is the line stays the same slope, but it moves into different places. And that's just because of the way that these linear equations work. If I collect to get all these points are here working, and when I sub the coordinates into 2x plus 3y, they all work up to different answers. And all the ones where it works out to -20 are here, and all the ones where it works out to -10 are here, and all the ones where it works out to 0 are here, and all the ones where it works out to, and so on. Okay, so different answers will work out to different things. And if I change what these numbers are, then I will get different equations again. And that will change the slope. And one way of trying to draw these lines for yourself, if you do feel like drawing them, is to try and figure out where they cross the x-axis and the y-axis. So I know that the x-axis has its own equation. The x-axis is the place where y is equal to 0, because all of the points on the x-axis have the y-coordinate being 0. And so I know that if I want to know where it meets the x-axis, I should make the y 0 and figure out what the x is that goes with that. So I'm just going to do a quick example on my piece of paper of calculating, of drawing one of these lines. So e.g. 2x plus 3y equals 9. The x-intercept is when y equals 0, and so you'll get 2x plus 3 times 0, which is 9. So 2x is 9, so x must be whatever 9 over 2 is, which is 4.5. Oh, that was only 3.5. One, 2, 3, 4.5. And the y-intercept is when x equals 0, which means that 2 times 0 plus 3y is 9, which means that 3y is 9, which means that y is 3 if I divide by 3. And so 1, 2, 3 there. And the line is a straight line, and it must therefore join those 2 points. And technically goes on forever. Ta-da! That's how you would draw one of these lines. So there is absolutely no need to rearrange this equation to any other format in order to sketch it. I just need to figure out 2 of the points are on it, and I'll be good. Okay, so that's what points in 3D, what an equation, linear equation in 2D does. What does it look like in 3D? In 3D, the points whose coordinates satisfy a linear equation form, well, what do they form? Well, let's do the same trick, right? I'll just leave that on the side. Here's my 3D. This is going to be my x-axis here, going that way. It's going to be my y-axis here, going that way. And this is going to be my z-axis up here. We're looking down onto it here. So, all right. Well, let's try and draw this. No. I'm going to draw this one. I'll put some marks in. 1, 2, 3, 4. 1, 2, 3, 4. And similarly up here, 1, 2, 3, 4 up here. Okay, so I can attempt to draw this by using the same sort of trick, right? So all the points on the z-axis line up with 0 on the x and 0 on the y. So if I want to find where it meets the z-axis, I should figure out when z is 0, when both x and y are 0, which means z would be 6. Whoops. I might just, don't have enough room for that. I'll just add some extra ones and make. Okay, so z equals 6. It's about 1, 2, 3, 4, 5, 6, about there. Give me a second. Of course, I didn't bring any. It's about there. It's a little bit of Play-Doh at the z equals 6. Okay, so the y-axis happens when lines up with 0 on the x, and also lines up with 0 on the z. So if x and z are both 0, the y would be 2, which is here. And if y and z are both 0, that would give me a place on the x-axis, which means, no, just 3. 6 divided by 2 is 3. And then this one would be 6 divided by 3, which is 2. And so okay, so those three things are there. All right. And I could attempt to try and find out what other points satisfy this. I guess if the x was 1 and the y was 1 and the z was 1, that would work as well. Okay. So that's about just there. All right. And if the x was 1 and the y was 2, then that would be getting us up to 5. That would be getting us up to 7. So the z would have to be minus 1. That would be under the plane. 1, 2. That would be down there. And if the x was 1 and the y was a half, that would be getting us up to 4, and the z would be 2. 1, a half, 2. Okay, they're all sort of filling in this little triangle here. So that happens, that's how it works. It's going to be a plane, and that plane is going to meet all three of these points, like that. And that'll always happen. If you have something with different x, y, and z coordinates, it will sit wherever it sits, and it will actually go on forever. But playing cards are a good thing to be planes. Planes are sort of flat, like a piece of cardboard, but technically they go on forever everywhere. Okay, so I'm just going to write that actually on the piece of paper so that it's easier to talk about. So, form a plane. Okay, so e.g. Sketch the plane with equation, what was it? 3x plus 2y plus z equals 6. This is going to be a very bad sketch. x, y, and z. So the x-intercept would be 3x equals 6, x equals 2. The y-intercept would happen when 2y equals 6 because the x and the z are both 0, which means y equals 3. And the z-intercept would happen when z equals 6. And so the plane would definitely pass, I'm just going to draw it in colour, through these 3 points. So the plane is the triangle extended. So it would go that way and this way and that way. It goes in all directions, but it's that sort of shape. Okay, we tend to draw planes in 3D as rectangles rather than triangles. So we would go sort of this way, and that way. Okay. So they're planes. So in 2D, an equation, all the points which satisfy an equation are a line, and so we would usually say that the equation represents a line. And in 3D, a linear equation represents a plane. Okay, so the question is, what are we going to do with this information? We should get a handle on some of the things we can look at just from the equation itself to tell about planes and lines. And so we've already seen something that I showed you. So some information. We know that if we change the constant term, this thing here, or here, it works with planes as well, then the two lines or the two planes or that you make when you do that are parallel. Now, they don't meet, but even better, it's not just they don't meet, they're the same slope. So the lines with equations ax plus by equals k1 and ax plus by equals k2 are parallel when k1 is not equal to k2. I mean, technically they're the same line when k1 equals k2, right? And they don't even have to be parallel. Any multiple of this will do. Watch this. Okay, no, wait. Leave it with that. If you just change this number, they're parallel. Okay, that's useful. And just as a drawing to go with that, they'll be like this. You know, or this, or whatever they are. Okay, so if this part is the same and these numbers are different, then the two lines are parallel. It also works for planes. ax plus by plus cz equals k1. And ax plus by plus cz equals k2 are parallel if k1 is not equal to k2. And normally you draw it like this, like that. So you imagine that your two planes are two playing cards that are in the same direction. So the drawing's sort of a picture of, the drawing on the page is a picture of this. But they're supposed to go on forever, but we only draw them as this much. In the same way as these lines go on forever, but we only draw them that much of it. Okay. So that's the first piece of information that we have. That parallelism happens when the two coefficient, two parts with the x, y, z are the same, but the numbers that they work out to are different. And also, I mean, if you multiply the entire equation by the same number, it's the same equation, because the same points will satisfy it. I mean, so look at this. If I multiply all of these by 2, let me just draw a whole new one. 4x plus 6y equals 18. It's the same line. And the reason is, well, if 2x plus 3y was 9, then multiplying one left side and the right side by the same number would give you the same equation, and so the same points will satisfy it. And that is always true. So the lines AX the equations AX plus BY equals C, and MAX plus MBX Y is MC for some m not equal to 0. The equations are the same line. Oh, sorry. The equations AX plus BY equals C and MAX plus MBY equals MC for m not being 0 are equations of the same line. Because, of course, if m equals 0, you get 0 equals 0 and everything satisfies that, and that's the entire plane. I always wonder what would happen if I wrote that in Desmos. Nothing. It's too clever. All right. So what that means is I can combine this with this. If multiplying the entire thing by the same number means it's the same line, and then changing what the final answer is means it's parallel, that means that you can actually tell always when they're parallel is if these parts that are with the x's and the y's, if they're multiples of each other. Okay? So lines with equations AX plus BY is K1 and MAX plus MBY is K2, and this is not a multiple of that. A parallel when K2 is not MK1, and the same line when K2 equals MK1. So that's the big rule that we can look at now, and we can just use those two bits of information. And it works for planes too. So for planes, X plus BY plus CZ equals K1, and MAX plus MBY plus MCZ equals K2, a parallel and K2 is not M lots of K1, and the same plane when k2 is mk1. And look, the idea is that if any one of them is not a multiple of the others, then if any one of the numbers that coefficients of x and y or z or whatever are not the matching multiple of the other, then they're not parallel. So just as a proper example of this, just to be absolutely certain that we know what's going on here. This plane, the planes with equations, that and this, 6x are parallel since parallel. And the reason we can tell is the coefficients of x are -3, which times 2 is 6. And the coefficients of y are 1 times -2, times -2, which is -2. And the coefficients of z, we've got -4 times -2 equals 8. And so -2 times each of these is each of those. But the constant term, 7 times -2, which would normally be 14, but it's not the 10. And so if this had been a -14, sorry. If this had been a -14, these are actually the same plane. But since it's not -14, they're different planes, but they're parallel. And e.g. the planes with equations 3x minus 5y plus z equals 5 and 2x plus a half y. You can have a half there. It doesn't really matter. Six are not parallel. Since the coefficients of z, we have 1 times 1 equals 1. And the coefficients of x, the first one times 1 would be 3, which is not 2. So the scalar multiple, the multiple of this coefficient that we need is 1, and the multiple of this coefficient that we need is actually, well, it's not 1. If we do that same coefficient on the other ones, we don't get the coefficient we should. And you don't normally have to give reasons for this. You're allowed to just say it's parallel or it's not parallel just by staring at them. Okay. Cool, so we can tell if they're parallel from the coefficients of the equations. And now we are up to the next bit. So that's all well and good. If we have two lines or two planes, we can tell whether they're parallel or not. The question is, can we tell where they meet? Can we tell where they meet? And what we'd like to do is find a way of telling whether at the points where these lines meet. So I'm just going to do it in 2D. 2D. Where lines meet. Okay. So well, let's have a look here. So that was my original equation. Let's draw another equation. That's another equation there. I might change its colour so it's a different colour from the other one. Okay, so that's the line x minus 4y equals 10. And we can imagine that at every other point in the plane, x minus 4y works out to a different answer to 10. It works out to, say, so at this point, x minus 4y works out to 0. At this point, x minus 4y works out to minus 15. And they all work out to different answers, but the points on this line, x minus 4y works out to 10. And the points on this line, x minus 2x plus 3y works out to 9. And so what I would like to do is find out where these lines meet. Now my graph, my computer here tells me that it's at the point 6 minus 1. But the thing I want to point out very carefully is that all of these points, x minus 4y works out to 10, and all of these points, 2x plus 3y works out to 9. So this is the point where 2x plus 3y works out to 9, and simultaneously x minus 4y works out to 10. That is the point that satisfies both equations at the same time. Because the only way to be a point on one line is to satisfy its equation, and the only way to be a point on the other line is to satisfy its equation. So if you are a point on both lines at the same time, you must satisfy both equations simultaneously, which is why they call them simultaneous equations. Let's find where two lines meet. Solve the simultaneous equations. And it's easiest to do in an example. Now, this example I'm going to give you a method which is not the final method we're going to have. This is just a beginning method which will help to make sense of these things. So find where the lines with equations 2x plus 3y equals 9 and x minus 4y equals 10 meet. So the points that we're looking for are points that are on both lines simultaneously. So I'm actually going to explicitly say that in my working. And I'm actually going to give the point some coordinates. Any point x, y on both lines satisfies both equations simultaneously. So equals 9 and x minus 4y equals 10. Okay, so it satisfies both of those equations at the same time, which means it must satisfy any multiple of the first equation and any multiple of the second equation. Okay, so it's got to satisfy, if 2x plus 3y is 9 for this point xy, then it must also be that 4x plus 6y is 18 as well. And it must be true that if x minus 4y is 10, then 2x minus 8y is 20, because it has to, it satisfies those. And you'll note it's very subtle, but we've switched from these equations representing all possible combinations of x, y that work to being just the specific ones that satisfy both simultaneously. So if it's true that both of these are true, then it's also true, for example, that also minus 2x plus 8y must be minus 20 as well, because we multiply this one by minus 2, and it's the same equation, really. It has anything that has x minus 4y being 10 would have to have minus 2 times one side equal to minus 2 times the other, because multiplying equation by something doesn't change what the solution is. Okay, well, another equation move, I mean, that's an equation solving move, right? An equation solving move is to multiply both sides by the same thing. Normally, you try and make it simpler when you do that, and I've actually just made it worse, but I've been very careful in the choice I've made, because the other equation move that you can do is to add the same thing to both sides. So I could add the same thing to each of these two sides, and it wouldn't change the answer. But did you notice that this is equal to this? So I could add minus 20 to both sides if I wanted. Well, watch this. Now 2x plus 3y is 9. So 2x plus 3y minus 20 is the same as 9 minus 20. Totally thing I can do. I'm allowed to subtract 20 to both sides. But I just said that this is the same as minus 20. So I can do this. I can replace the minus 20 with that, because they're the same. And now 2x minus 2x is 0, 3y plus 8y is 11y. It's minus 11, and so the y must be minus 1. And now if the y really is minus 1, then that should allow me to figure out what the x is as well. But are you ready for a magic trick? Ready? It's really cool. y must be minus 4. If y is minus 1, 4 times y must be minus 4, which means that x minus 4y... Now, x minus 4y was 10. Do you remember that? Yeah? And so x minus 4y plus 4y must be 10 plus 4y, because I'm allowed to add the same thing to both sides, which means that x is... But just a second, just wait. 4y is the same as minus 4, isn't it? And so x must be 6. So the point xy, which is on both lines, must be 6, negative 1. Now, I didn't do traditional moves here, right? This is not how you would normally do this. All right? So this is not the final method we're going for. Just pointing that out, okay? But what I wanted to say was that because I know that it satisfies both of these equations, I can do some pretty fancy little tricks to figure out what's going on. This little trick here where I added minus 20 to both sides, but then noticed that minus 20 was the same as this thing, and so I replaced it there. It's a very nice trick. And what most people do is they don't actually do all of that at once. They just do this bit where they add one side of this equation and the other side to the other side. So it turns out that what we can do with linear equations is we can add these two sides and add these two sides, and it will still be correct. And that's pretty cool, I think. It's a sweet little move. And back here, I could totally have put the y equals minus 1 back into this formula to get x plus 4 equals 10, and therefore x must be 6. But I could also do it with that same little move. I can add 4y to both sides, but notice that this 4y could totally be the same as minus 4. So that's what I wanted to get at. that we can now do moves with these linear equations by just adding the equations together as if they were like coordinates of something. And this is where we get to the really cool trick that people, oh gosh, maybe about 100 years ago, figured out this really cool way of solving linear equations that didn't require all this messing around with the x's and the y's. Because we know that when we add these things together, we can just sort of add the x's and add the y's and add the numbers. And in that case, the x's don't really even need to be there because they're just holding those numbers in place. So if I had a different way of holding those numbers in place, I could make that work. And a different way of holding numbers in place is with matrices. That's what a matrix is for. It's an array of numbers which, you know, are held in place by being in certain positions in the array. So I can solve simultaneous equations with matrix methods instead. So these moves can be done with row operations on matrices. Okay, so I'm going to do an example, and then I'm going to tell you about the row operations, and I'm going to do another example, and then I'm going to do it in 3D. Okay? Cool. Good-o. So let's do this one again. With equations 2x plus 3y equals 9 and x minus 4y equals 10 meet. Okay, so this is going to be the sort of, in inverted commas, proper version, the sort of thing that if I asked you to do an assignment or, you know, another teacher asked you to do an assignment, is the sort of thing that they would want you to do. Okay. So I'm going to set up a matrix using the coefficients. So the first equation, we'll use those numbers, and the second equation, we'll use those numbers. So what we did is we stole the 2 and the 3 and the 9, and we put them in this row, and we stole the 1 and the minus 4 and the 10, and we put them in this row. Okay, so each equation became a row. All right, and just to remind myself, this is the x's, the coefficients of x, these are the coefficients of y, and these are the plain numbers. Now, I will say something. It is tradition to put a bar here to keep track of which bit is the coefficients and which bit is the answers. It's not necessary, but it's traditional, so if someone's watching you do this, they're going to be a little bit confused if you don't. And I should say that this matrix is called an augmented matrix. The reason it's called augmented means, you know, have had something attached to it, something it's been made bigger. An augmented matrix is that some people, when matrices were sort of first invented, this bit, the bit with the coefficients was the bit that had the matrix, and then this was a separate extra bit, and it's been tacked on the end. Okay, now what we're going to do is we're going to do row operations, because row operations are the same as doing equation solving. Okay, so the philosophy here is that there's always going to be 2 equations, and I'm going to keep 2 rows in my matrix all the time. Back in the other one, I was flipping things around and putting back together and whatever, and I'm going to do that, but I'm always going to keep 2, because we always need 2 equations to specify what we're going to do. Even at the very end of my working, I ended up with 2 equations. One of them was y equals minus 1, and the other one was x equals 6. And that's still 2 equations to specify what my point is. Okay, so that's what I'm going to do. So what did I do last time? I multiplied this one by 2 so that I could subtract it. And I might do that. My new row 2 is minus 2 of row 2. And then I added these 2 rows together to make a new equation. And I'm going to have to keep one of them because there always have to be 2. So I'm just going to keep this one because it's prettier. And so I'm going to have my new row 2 is my old row 2 plus is this row 2 plus this row 1. So this is the method that our friends worked out. Okay. And now I can see what y is going to be. I'll divide by 11. So my new row 3 is, so just to point out that because we're now working with matrices, there is no such thing as division by a number. I have to do it as a multiplication. Okay. So now at this stage, I want you to realize that that final row is saying that there's that 0 x's, because it's still x, 0 x's and 1 y is minus 1. So this row at the moment is telling me that y equals negative 1. So you normally wouldn't put these things in clouds in your working. Okay. Now, in my other working, I combined this with this equation that I had here. But that equation is in a whole different matrix. I've lost it, so I'm just going to combine it with this equation here. So what did I do? If I make this minus 3, then they'll match, right? But it turns out you can do all of that in one go. Okay, so if I multiply this one by 3 and then went this row minus 3 of that row, that'd be great. But then I wouldn't have my pretty 1 and minus 1 here that gives me what tells me what y is. So we're going to allow ourselves to do a row operation like this. Why am I calling this row 3? It's only row 2. Sorry. So my new row 1 is my old row 1 minus 3 lots of row 2. I'm going to do all of that in one go. Okay, let's see if I can do it. No, I can't be bothered. I'm just going to write down the working. This is what row 1 is. 2, 3, 9. And this is what minus 3 of row 2 is. 0, minus 3, 3. And so when I add them together, I am going to get my new row 1 is going to be this plus that, which is still 2, 0, 12. So the point is that I do all of this in one go, and I don't lose this row that I just made. And then I'll divide that 1 by 2, but technically I have to multiply by a half. And now this row, I'm thinking, means that x is 6, because it's 1x and 0 y's is 6, which is the same as just saying x is 6. And so therefore, I can say x equals 6 and y equals negative 1. So 0.6 minus 1 is on both lines. And I would only expect there to be 1 point on 2 lines. Yay! Okay, that's the process that our ancestors came up with, and it's pretty slick. And it's sort of copying some of the things that we're allowed to do with equations, but trying to be really precise about the things we're allowed to do so that we can not worry about them so much. Okay. All right. So you'll notice a couple of things if I point them out to you. I had two basic row operations. I was able to multiply rows by stuff. I was able to add them together, or I could simultaneously have a row and add or subtract something from it. Now, conceivably, I could have like some number of row 1s and some number of row 2s and combine them together, but there are some technical details in the theory in the background that mean that that's going to make it hard to keep track of what's going on and keep track of whether the solutions are really working the way they should. So we're not going to be allowed to do that one. If you want to do something where you change row 1, then you have to have the row 1 without a multiple. But you can put the other rows on there if you want. Okay, cool. All right, that's great. So the process comes out like this. The algorithm becomes each row, each equation becomes a row in an augmented matrix. Do row operations. Okay, and the row operations that are allowed are new row I is some multiple of the old row I, where I is whichever row you're doing. New row I is the old row I plus some multiple of some other row, or minus, doesn't really matter, but then the m is just negative. And technically there is one other operation you're allowed to do, which is that the new row I and row j is the old row j and row I, where you're allowed to swap rows around. Because, I mean, really, just swapping the rows doesn't change what the list of equations is, and so you are allowed to do that. Okay, these are called elementary row operations. And 3, well, you need a goal. You want to get as close to 1001 as possible. It doesn't really matter what's here. And then read off the answer. So that's the algorithm we just did. It doesn't really matter what row operations you do, as long as they're only elementary row operations. You can do them in whatever order you like. I find it productive to create one column of this at a time. That's what I like to do. And I find it productive to make the 1 and then make the zeros. So just some advice. Make one column at a time. 1 and then 0. But, I mean, whatever you want, doesn't really matter. Okay, cool, nice. That's the process. Now, for 2 lines in 2D, there's not much of a problem going on. Okay, it's not going to be an issue. We're going to be able to create whatever we want. It's going to be pretty straightforward. There's only a couple of options for what could happen. So your 2 lines are going to be parallel, in which case you don't really need to solve the equation. You know there's no points in common to start with. Or you can do this to find the solutions. In 3D, it's a little harder to tell what's going on. I mean, obviously, if there's only two of them, then they'll be parallel, or they won't be. That's going to be tricky. We'll get back to that in a minute, just a second. I would like to do another example to just sort of illustrate something useful about this. For which k do the three lines x plus y equals 7, 2x minus half of y equals, just a second, going to pause, k equals 9, and 7x plus ky equals 39. Pass through the same point. Okay. Now I had two lines before, and I wanted to find out where they meet, and so I had two simultaneous equations. Well, what if I had three lines? Any point which was on all three of those lines would satisfy all three of those equations simultaneously, and so I need to solve those three simultaneous equations. So solve. So if xy is on all three lines, then it satisfies all three equations, which would be x plus y equals 7, 2x minus a half of y equals 9, and 7x plus ky equals 39. So I can set up an augmented matrix. So there's nothing stopping me doing this. 1, 1, 7, 2 minus a half, 9, 7 k 39. And it's okay to have three rows. I'm just going to have to look to see what's going to happen when I do my row operations. So as I said in my advice, I'll create one column at a time. So I'm going to get 1 and then going to make these ones 0. Okay, so let's see, my new row 2, I can take off 2 lots of row 1, like that. So let's see, this is what row 2 currently is. And minus 2 lots of row 1 would be minus 2, minus 14. And so my new row 2 will be 0, minus, so minus a half plus minus 2 would be minus 5 on 2. 9 minus 14 is minus 5. Okay. Now it should be okay for me to do the same trick in row 3 because I'm not using row 2 to change row 3 at the same time as changing row 2. So I reckon I'm going to do this as well. New row 3 is row 3 minus 7 of row 1. So this is what row 3 is currently. This is minus 7 of row 1. Minus 7, minus 49. Okay. And this must be what my new row 3 is then. So let's see, this plus this is 0. This is going to be whatever k minus 7 is, and minus 10. Okay. So my new matrix is this, 1, 1, 7. I didn't actually change row 1. My new row 2 is 0, minus 5 on 2, minus 5. My new row 3 was 0, k minus 7, minus 10. Whoop, sorry. Okay, rightio. So I've made my first column. That's all good. That's great. So I'd really like there to be a 0, 1, 0 somewhere. I might as well pop it here. Okay. So my new row 2, if I multiply this by minus 2/5, then that will produce a 1, because minus 5 over 2 times minus 2 over 5 would give me the minus minus, 10 over 10, which is plus 1. So we should get 1. So minus 2 over 5, so that'll be 2. Okay. This is interesting. This is interesting. I think I've done something wrong here. I think something bad has happened. I'm just going to check something. So my new row 2 was row 2 minus 2 of row 1. So minus 2 minus 14. Minus 2 minus a half is minus 2.5, which is minus 5 over 2. Yeah, that's fine. So 3 is 7k, that. Minus 7 minus 7 minus 49. Nope, it's all working fine. Okay. Well, I've noticed that if k is 7, I'm going to have a real problem. Because if k is 7, I'm going to have 0x plus 0y is minus 10. So let me just, I notice this. If k equals 7, 0, 0, minus 10, which is the equation 0x plus 0y equals minus 10, which is 0 equals minus 10, which doesn't make any sense. There's no solutions. Okay, so k definitely can't be 7. If they're going to meet. So if k is 7, there is no point that's in all 3 planes, or all 3 lines. Just going to type some things in the computer. That's what the 3 lines look like. Yes, okay. Actually, they're parallel. Oh, of course they are. Look, look, look. The original equations, if we've got x plus y equals 7, 7x plus 7y, that'll be parallel to the original one because it's times 7. Okay, so if k is 7, 2 of those lines are parallel, and so they're definitely not going to meet. In fact, equation 1 and equation 2 are the equations of parallel lines. Okay, cool. So now what, though? Like, I mean, what are we going to do now? I suppose we're supposed to produce a 0 here and a 0 here. I mean, it's traditional to have everything zeros except for these ones. And we need a new notation, actually. These are called pivots. So I'm just going to go back here. These ones are called pivots, just so you know. Okay, so that's great. So I guess I'll go back to here and I'll make a 0 there. So my new row 1 could be row 1 minus row 2. That'll work, won't it? And I don't think I even need to do any work for that one. I'll be okay with that. So we had 0, 1, and 2, and 1 minus 0 is 1, 1 minus 1 is 0, 7 minus 2 is 5. Okay, oh, sorry. So it looks like I can create, let me just do this. 1 minus 0 is 1, 1 minus 1 is 0, 7 minus 2 is 5. So it looks like we've got x equals 5, y equals 2. So if they're going to meet at the same point, it'll be the point x equals 5, y equals 2. Okay, cool. But I might also make a 0 down here. That's tradition. So my new row 3 is row 3 minus, well, just a sec. Just because that's k minus 7 doesn't mean I can't do this trick. So let me just do that properly. My row 3 is currently 0, k minus 7, minus 10. And minus k minus 7 lots of row 2 is 0, minus k minus 7, and minus 2 times k minus 7. Okay. And so my new row 3 is 0, 0, and whatever this works out to be. Where x is minus 10 minus 2k minus 7, which is minus 10 minus 2k plus 14, which is 4 minus 2k. Which I've noticed is 2 times 2 minus k. Okay, so we've got 0, 0, 2 times 2 minus k. Well, now we have a similar problem than we had before, actually, because if I've got 0x plus 0y equals this, the only way that that's going to work is if this is 0. So the final row is 0, 0, 2 minus k, which is the equation 0x plus 0y is 2 minus k, which is that 0 is 2 minus k. So 0 is 2 minus k when I divide by 2, and so k has to be 2. Okay, so if k is anything other than 2, there won't be any solutions. If k is not 2, then 2 minus k is not 0. And there are no solutions. But if k is equal to 2, then the matrix is 1, 0, 5, 0, 1, 2, 0, 0, 0. And the solutions is that x has to be 5 and y has to be 2. So it turns out, so if k equals 2, the three lines are x plus y equals 7, 2x minus a half of y equals 9, and 7x plus 2y equals 39, and they all pass through 5, 2. But if k is not 2, now we don't have to say k is not 7, because, well, if k is 2, k is not 7, and if k is not 2, all right, we can do that. If k is not 2, there is no point in all three lines. Okay. Now if k was 7, that was because two of the lines are parallel, and if k isn't 7, then they don't have to be parallel to do that. Let me just show you something. I'll go back to the computer. So that's the parallel one. If k is 2, yes, they all pass through this point just here, which is the point 5, 2. And if k was like 1, well, then they don't all pass through the same point at the same time. Like the red one and the black one meet here, and the red one and the purple one meet here, and the black one and the purple one meet here, but there is no point that's in all three at the same time. Let me just put a 10 there so that the gap's even bigger. Like a -8. Okay, so no matter what other one I pick, they make a little triangle. But either way, whether k is 7 or k is not 7, but not 2, then there's still no point in all three. Okay. Right. Okay. So I guess the point I wanted to make there is that if you move some of the lines around, you can get different results for what's going on. Actually, I do want to make one more point about moving lines around. See this thing back here, this version here. At every stage in this process, I had a different pair of lines than the ones I started with. Let me show you. So I started with 2x plus 3y equals 9, and 1x minus 4y equals 10. That was my first matrix. Then my second matrix was still 2, 3, 9, but it was minus 2, 8, and minus 20. Minus 2 plus 8 and minus 20. Now, that didn't actually change anything because I just multiplied that row by something. But now at this stage, I've changed it to 0, 11, minus 11. So there's no x's. Plus 11y is minus 11. And now I've moved my line to a new spot. But I haven't changed what the intersection point is. It was in the same place it was before. I'm just going to mark that point for you so that we can see that it's not moving. And then my next equation had 1 minus 1. Which is the same line. That's great. And my next equation was 2, 0, 12. Which is a vertical line now. And then my next equation was 1x is 6, which is the same vertical line. So what I've slowly done is I've moved the lines without changing the intersection point, so it was a lot easier to tell where the intersection point is. So I just wanted to say that if you want to say anything about whether they're parallel or not, you have to go back to the, we have to go back to the original equations to tell whether they're parallel. And we could tell these ones weren't parallel right from the start, because this one is 2 times that, but this one is not 2 times that. Okay, so that's lines. Well, now we want to know what's going on in 3D. So, what is going to happen in 3D when I do these things? 3D, where planes meet. Now we're going to use the same process that we used before, but it's going to be a bit more complicated now because there's 3 variables involved, and we might have more than two equations, but we've already dealt with that. So first, we know how to tell if 2 planes are parallel. And we know if they're parallel, they're not going to have any points in common. So let's think about how 2 planes might meet. Two planes in 3D. So options are, they could either technically be the same plane. We've already covered that. We know how to do that one. They could be parallel, which will happen. We know how to tell that one. That is a bad move because they're different sizes. I mean, technically they both go on forever, so it doesn't really matter. So they could be parallel, so they could look like that, or anything where they're the same direction, or, you know, whatever, and going on forever. In which case there are no points in both planes. Okay. Or they could meet in a line. So if 2 planes aren't parallel, right, and this one's sloping that way, let me do it this way. This one's sloping that way, then if I follow where that plane goes, it's going to hit the other plane. And in fact, if I extend it and then keep extending it, 2 planes in 3D that are not parallel must meet in a line. There must be a line that is in both planes simultaneously, a whole line's worth of points. There is no other way around it. It has to be that way. Oh, how am I going to draw this so that it doesn't look like crap? I'll draw one of them there and the other one there, like that. And here's the line of intersection. And since there is an entire line of points that they share, and because the planes go on forever, the line goes on forever, that means there's infinitely many points. So back when we were working in 2D, only 2 things could happen. We could either get no points in common, there'd be no solutions, and we actually noticed when those no solutions happened. They happened when you got an equation that was like 0, 0, 0, something not 0. So we can definitely tell when there's going to be no solutions. The question is, how are we going to tell when there's going to be infinitely many solutions? It's going to be tricky. It's going to be very tricky. So, all right, it's going to be interesting. Let's see what we can do with 2 planes and move one of the planes by changing its by changing, no, I'm not going to do that at all, sorry. 2 planes in 3D. The only other situation we have, there's either none or infinitely many. And so, I mean, we can tell when we've only got 2 planes, they're either parallel or they're not parallel, in which case there's going to be infinitely many points in both planes. So there's really, with 2 planes, no other options, and so we don't have to worry about even doing these row operation things. We can just look at them and say, aha, parallel, great, no points. Not parallel, infinitely many. Finding out exactly which points they are is going to require us to know a little bit about vectors and a little bit about line equations, and so I don't want to go there. That's sort of beyond the scope of what we're going to do today. Okay, so I'm not going to go there, but I am going to talk about what happens with 3 planes. or possibly more than 3. It gets more and more complicated the more of them you have. Okay, when there's 3 planes in 3D, they could all be parallel. That's totally possible. My planes are getting less and less rectangular. But even if you just randomly picked points, it would be picked coefficients to go with your x, y, and z. That's going to be way hard. So 3 planes being parallel, totally, I can do it. Ta-da! Or ta-da! All parallel, perfectly fine, and there's no points that are in all 3. But you actually only need 2 of them to be parallel to not have any points in all 3. You could have a third one sort of slicing down and meeting both of the others. Like that. And as long as these two are parallel, it doesn't matter what the other one's doing. There's never going to be a point in all 3 because there's not a point in just these 2. If I look at those 2, they meet in a line. Have a look at those 2, those meet in a line. But these 2 still don't meet at all, so there can't be any points in all 3 of them either. And there is one more way to arrange 3 planes and have no points in common at all. And it is this. We have one plane there, that's the tables on the table, and these 2 planes. And like that. Those 3 planes still have no points common to all 3. Now, sure, I'm just going to line them up vertically. It's going to be tricky. My card house building skills. Like that. As a triangle. Those 2 meet in a line. Those 2 meet in a line. Those 2 meet in a line. But there is no point in all 3 of them at the same time because of that big tunnel right down the middle. It's a bit like a Toblerone box is the same idea. So they could be arranged as a triangular prism, in which case they're non-parallel, but they're in a triangular prism, in which case the easiest way to draw it is to draw the triangle and then extend everything. Like that. So these 3 here have no points in all 3 planes. Okay. But all of them, if you do row operations on your matrix, they will all produce a situation when you get 0, 0, 0, and then over in the numbers column, not 0. And they will be distinguished by the fact that all parallel you'll be able to tell from the original equations whether they're parallel. So, no points in all 3 planes will happen when my matrix gets something like this. 0, 0, 0, not 0. I'm going to write this again in a minute. Actually, do you know what? I'll write it again in a minute. I won't put it here. But these are distinguished by the original equations. Okay, so I can tell this from the matrix. from the row operations. And this from the original equations. So these two will be obvious from the beginning. You'll be able to tell if there are parallel planes, and you can just say, there are parallel planes, I'm stopping now, I don't have to do any work, I can tell that there's no points in all three. This one, you won't be able to tell from the original because they're not parallel to each other. Okay, so there's no points in all three planes, that's a possibility. It may be that there is exactly one point in all three planes, and you see this situation every single day. You see it when you see the corner, when you're standing in a room and you see the two walls and the floor all meeting, and there is one point that's in all three of those. So look at this, that's the floor, that's a wall, that's a wall. There is only one point that's in all three of those planes, it's this point down here. This line is where those two planes meet, and that line can only meet this plane in one point. I mean, and they don't have to be nearly so neatly arranged. You know, they can be like this. They can make a really skinny angle like this, and the third one crosses them there. Or the third one could come across the other two. I don't really want to cut my cards. Could come across the other two like that, and there's still one point in all three. Like, they don't have to be neatly at right angles for this to work. But that there is the single point that's in all three of them. And when mathematicians talk about single or only one, they use the word unique. There is a unique point in all three of the planes. And you can tell this from the row operations as well. And finally, there's only one other way that three planes can meet, if they're three properly different planes. I mean, obviously, if two of the equations are multiples of each other, you've only got one plane. There's only really two of those planes are actually the same plane, in which case it comes down to just really being two planes. So with three planes, it is possible to get infinitely many points in common because they could all pass through the same line. They all pass through a shared line. Now, let's see if I can draw that. I'm going to have one here, and one here, and one here. Drawing planes is an acquired skill. In which case, there are infinitely many points in all three planes. Okay, so that's how planes can be arranged in 3D and to get the various different numbers of points in common. And what we talk about with the equations is that the planes have points in common and the equations have solutions. Okay, so when we get some planes, to find these, this is the algorithm. So set up an augmented matrix, just like before. I'm going to go back and copy what I said for the other algorithm, actually. So each equation becomes a row. Okay, and then do row operations. And it's especially important to do elementary row operations when you're in 3D because more crazy stuff can happen if you don't. But I'm actually going to write them all down again here because it's nice to have them in two places. Don't forget that you can always multiply a row by something because that doesn't change what things solve that equation. And you can do this trick, which was the fancy trick, where you go row I plus some multiple of row j, and then you can always swap two rows. Because that's just listing the equations in a different order. All right, and what we want to do is we want to get to having columns with ones and zeros. And then read off the answer. Oh, and it's not going to be that easy. What we're going to do is we're going to attempt to make pivots. And a pivot is going to be a 1, which is in the position you would expect it to be for a column of the identity matrix. So, for example, 1, 0, 0, 0, 1, 0, 0, 0, 1 has 3 pivots. There. Or, for example, you might have 1, 0, 0, 0, 1, 0, something, something, 0 that has 2 pivots. It's technically also possible to get 1 pivot. Okay? And technically, if you're making, you will be able to tell where the pivots are without putting zeros above. So if all you're doing is looking for where the pivots are, you don't need to put the zeros above. If you want the solution. If you just want to know where the pivots are, you can just make the ones in those spots. You don't even need to make the ones. As long as they're not 0, it should be okay. I'll talk about that in a minute. And then look for these situations. Now we know that if you get any row at any stage, which is this, then there's no solutions. Okay? So solutions are referring to the combinations of x, y, and z that are possible. No solutions for the equations, which means no points in all 3. In all 3 planes. Second thing you might look for is there being a pivot in every column. And you can tell when there's going to be a pivot in every column. You don't have to actually produce the ones as long as it's possible to produce the ones in the future. From what you've got, it should be okay. Anything that looks like this, not 0 here, not 0 here, not 0 here, and these don't care what they are, and these are 0, and these are whatever they are, then that will mean that there is exactly one solution. which means that there's one point in all three planes. And anything else that is not that will be infinitely many. Okay? And if you look very closely, infinitely many will tend to happen when there's a row of zeros here that will prevent there being a pivot in that position there. Anything else, i.e. 0, 0, 0, 0, prevents a pivot, then that means there's infinitely many solutions. Please do not say infinite solutions. The solutions themselves aren't infinite. They're just, like, each individual solution isn't infinite. So the solution itself is just a single point. It's right there. It's not infinite. It's just little. So you can't say infinite solutions because it's not clear what the infinite refers to. So you have to say infinitely many solutions. Which usually means, if you haven't already checked for parallelism, that they meet in a line. And then number 5, you should just check for parallelism. From the original equations. So that's the algorithm that we can set up for trying to figure out how planes meet. If you want to figure out exactly what that point is where they meet, if they do end up meeting in one point, then you're going to have to finish it off to get all the way to here, and then you'll be able to tell. So check parallel from original equations, or finish the row operations to find the point. Okay. Let me do an example or two. So let me do a specific example with specific planes. So decide how many points are in all three of these planes. X plus 3y equals 10, x minus y plus 6z equals 15, and 2x minus 2y plus 12z equals 85. And the answer is none, because plane 2 and plane 3 are parallel. That's it. No need to do anything else. There aren't any. I will point out here that it is okay not to have a z. It's actually okay not even to have a y. You're allowed to just have x equals or y equals or z equals. Just pointing that out. Now that was a bit unsatisfying. So let me just come up with another one. So I'm just going to do another one. Okay. Solve these equations, interpret the result geometrically. Okay. X minus 3y plus 4z is 10. Two x plus 5y plus 8z equals 20. And 3x minus 8y plus 12z equals 5. Okay. So let's see. We'll set up an augmented matrix. One now. Let's see, there's going to be an x, there's going to be a y, there's going to be a z, and then there's going to be a number. So we have 1, minus 3, 4, 10, 2, minus 5, 8, 20, 3, minus 8, 12, 5. Okay, so I could make zeros here, and I normally work one column at a time. Just going to kneel down on the floor. So my new row 2 is going to be my old row 2 minus 2 of row 1. And just so that I don't have mistakes in my working, I'm going to do this. This is row 2, 2 minus 5, 8, 20. Just let me check something. Well, these two aren't parallel because they would be if there's a 2 here, but this isn't 2 times that. These two aren't parallel. Well, they would be, I mean, this times 3 and that times 3 works, but this times 3 doesn't match. And these two aren't parallel because this one would be times 1.5. That's also times 1.5, but 1.5 times 5 is not minus 8. Okay, so none of them are parallel. Okay, good. So the options are either they make that triangle, in which case there's no solutions, or they're going to be all creating one exact point where they all meet. Okay. So minus 2 row 1 is minus 2 of this, 6, minus 8, minus 20. Okay. And so then my new row 2 will be 0, 1, 0, 0. Ooh, interesting. That's telling me that y is 0. If they're going to meet, that's the coordinates of the y coordinate of the point. Fascinating. And let me do new row 3, being row 3 minus 3 of row 1. That'll work here. If there's a 3, 3 minus 3 times 1. I should point out here that you're not allowed to just subtract 3 from every point. It's not how it works. You have to do it as whole rows. So let's see. This is what row 3 is. Minus 3 of row 1, minus 3, 9, minus 12, minus 3 of row 1. That's minus 30. And so my new row 3 is going to be 0, 1, 0, and minus 25. Ooh, interesting. So my matrix is now 1, minus 3, 4, 10. My new row 2 is 0, 1, 0, 0. My new row 3 is 0, 1, 0, minus 25. I can see a problem. Let's put a 0 here. Sorry, here's my matrix. Let me just check if I've got that right. The old row 1 was 1, minus 3, 4, 10. 1, minus 3, 4, 10. The new row 2 is 0, 1, 0, 0. Okay, so what if I do row... No, new row 3 is the old row 3 minus row 2. I don't think I need to do the calculation for this one. 0 minus 0 is 0, 1 minus 1 is 0, 0 minus 0 is 0, 0 minus minus 25 is 25. And I've created a row where I have 0x plus 0y plus 0z is 25. So the final row is 0x plus 0y plus 0z is 25, which is 0, which is this is 0 because 25, and there's no solutions. And so therefore, all right, so what does that mean? My original equations, there is no point in all three of these planes. So there's no solutions, and so I interpret the result. The original equations define three planes. Okay? So this is how to interpret a result geometrically. You tell the reader what the equations represent. So the original equations define three planes. And then you could say the solutions are the points that are in all three, but there are no solutions. So there are no points in all three planes. Now I also know that none of the planes were parallel. So they must be arranged in a triangular prism. Because that's the only way for three planes to be arranged in 3D space and not be parallel but still have no points in common. Okay? So I was able to stop at the moment I got a thing where there was no solutions. What if I had changed one thing about this matrix, about these equations? What if this had not been a 12, but had been some other number? Then when I did my working, this would not have been a 0 here. So I'm going to do that. In fact, I'm going to do a whole other thing, but I'm just going to point that out with that one. This one would not have been a 0, and when I did the subtraction, I would have gotten 1, 1, something other than 0, and I would have known there was a unique solution. So I'm going to do an example where there's going to be a unique solution just to show you how it works. Interpret the result geometrically. All right. Give me a second to come up with this. All right, let's do this one. I don't all have to be whole numbers, but it's easier for me to think of problems if I'm using whole numbers. So I'll set up my augmented matrix. 1 and It's got x, y, z, and a number. So let's see, I've got 1, 2, minus 3, 5, 0 x's, 5 y's, 4 z's, and an 8, 3 x's, 11 y's, 8 z's, and a 20. All right, well, as usual, I want to try and put as many zeros as I can in here. So I'll do my new row 3 is my old row 3 minus 3 of row 1. I don't have to worry about the row 2 because it's already got a 0 where I want it to be. So let's see. Do you reckon I can do that in my head? I'll give it a go. I didn't change row 1. I didn't change row 2. 3 minus 3 times 1 is 0. 11 minus 3 times 2, which is 11 minus 6, which is 5. 8 minus 3 times minus 3 would be 8 plus 9, which is 17. 20 minus 3 times 5 would be 5. Whew. Tricky. Okay. Now, normally I would make a 1 next. But I notice that if I do this row minus that row, I'll make a 0 in this position, which I'm going to need eventually. So my new row 3 is going to be row 3 minus row 2. And I can totally do that one without... okay, so 0 minus 0 is 0. So 0 minus 0 is 0. 5 minus 5 is 0. 17 minus 4 is 13. 5 minus 8 is negative 3. Okay, so I can tell at this stage that I'm going to be able to get a unique solution because I could divide by this 13 to get a 1 in that position, and I can divide by this 5 to get a 1 in that position, and I'll be able to eventually make zeros everywhere else to get everything else. So at this stage, I can tell there will be a unique solution. I need to keep going to figure out what the unique solution is, but I can tell that what the unique solution that there is a unique solution. So now I can tell there will be a pivot in every column. So there will be a unique solution. So if all I was asked was how many solutions are there and interpret the result, I could have stopped here. The original planes are not parallel. This one's definitely not parallel to either of those because if it was, there would be an x. And these two aren't parallel because this one times 3, that one times 3 is the wrong number. Okay. But I know that they can't be parallel if there is a solution at all. So if there is a point in all three, they can't be parallel. There will be a unique solution. Planes represent the equations define planes, and the unique solution is the single point in all three planes. If we continue our row operations, we can say my new row 3 is a 13th of my old row 3. And actually, I reckon I'll do my new row 2 is also a 5th of my old row 2. That's okay because I'm not using one row to affect another one. Beautiful. So let's see. My new row 1 is going to be row 1 minus 2 lots of row 2. So let's see, 1 minus 2 of this didn't change row 3. Whoa, minus 3 on 13. Whew, that would have been a disaster. This minus 2 of that is still 1. So, right, this minus 2 of that is still 1. This minus 2 of that is 0, which was the point. This minus 2 of that, so minus 3 minus 8 fifths. 3 is 15 fifths, so that's minus 23 over 5. And 5 minus 16 fifths, 25 would be 9 fifths. Okay, and then I can go, no, new row 1 is going to be my old row 1 plus 23 on 5 times row 3. Whoa. It's going to be tricky. And my new row 2 is going to be row 2 plus minus 4 fifths of row 3. So I'm using the position that's here as the multiple that's there because this is a 1. All right, so I didn't change row 3. So row 1 plus 23 fifths of row 3, that'll be still 1, still 0, 0. Oh, wow. I'm going to call them numbers. A is going to be 9 fifths plus 23 fifths times minus 3 over 13. So if I multiply this one by 13, 9 times 13 is 90 plus 27, which is 127. No, 117. 23 times 3 would be 69. So, oh gosh, minus 7 would be 47, 48. Okay, and then we go 0 plus minus 4 fifths of 0, 1 minus 4 fifths of 0, that'll be 0, and the b will be 8 fifths minus 4 fifths times minus 3 on 13. So we'll have 8 times 13, which would be 80 plus 27, which is 24, which is 104. And so that would be 116 on 65. So my solutions are that x is this, x plus 0y plus 0z is this, 0x plus 1y plus 1z is this, and 0x plus 0y plus, 0x plus 1y plus 0z is this, and 0x plus 0y plus 1z is this. And so I get the point in all three planes is 48 on 65, 116 on 65, minus 3 on 13. Yay! So the only other thing that would happen is that there would be something where you would get infinitely many solutions. So I'm going to do one more example before I do my final example, which will involve some unknown coefficients as well as the x, y, z not being known. So I just wanted to give proper examples that produced the results, all three of the possible results. How many solutions do these three equations have? Interpret your result. I'm warning you now, it's going to come out to have infinitely many. Okay? Because I want you to see what that looks like. So let's see. All right, let's see. Just a moment. Minus x plus 9y plus 2z equals 26. Okay. All right. Now, this one I'm deliberately trying to be a bit confusing. This one doesn't have a y. This one doesn't have a z. This one has all three. Just let me see if I can tell if they're parallel. If this one was parallel to that one, then this would be minus 2 times that, and we should have 0y times minus 2, so they're not parallel. Okay? These two can't be parallel, because if this one was parallel to that one, it would be some multiple of x, and we'd have the same multiple of z, so there should be a z, so they're not parallel. These aren't parallel because this one has a y and that one doesn't. These aren't parallel because this one has a z and this one doesn't. And these aren't parallel because this one has a z and this one doesn't. So they're not parallel. Okay, so none of them are parallel. So we're going to get solutions. Okay? Oh, sorry. That shouldn't be a line there. That's still part of the original problem. Well, we might not, of course, because if they're all three not parallel, it is technically possible for them to be arranged in a triangle. So let's just see what happens. We know what's happening because I set it up. You know what's going to happen. So we're going to have an augmented matrix. And so let's see. We're going to have an x and a y and a z and a number. So there's 2 x's, no y's, and minus 1 z's is 5. 5 x's, 3 y's and no z's is 12, minus 1 x's and 9 y's and 2 z's is 26. Okay. Oh, look, this one looks like it's going to be a bit trickier to get to the position I want. I can, if I move this row, minus this row and move it to the top, I can get the one that I'm hoping for. So let's do that. My new row 3 is minus row 3. Didn't change this row. Didn't change this row. I did change this row. Okay. And now my new row 1 and row 3 will be my old row 3 and row 1. I'll switch them around. So that was from my row 3. That was from my row 1, and I didn't change row 2. Okay. So now what I'll do is I will make zeros in these positions here. So my new row 2 will be row 2 minus 5 of row 1. And look, I am going to do this properly because I can tell I'm getting tired and I'm going to lose some minus signs. So let's see, this is my original row 2, which is 5, 3, 0, 12. This is minus 5 of row 1. So minus 5, 45, 10. 5 times 26, well 5 times 25 would be 125, so 130. And so my new row 2 is actually 0, 48, 10, and 142. Wow, that is big. Okay, and I might do new row 3 is row 3 minus 2 of row 1. So row 3 was 2, 0, negative 1, 5, and minus 2 of row 1 was minus 2, 18, 4, and 52. Okay. And so my new row 3 is 0, 18, 3, and 58. One minus 9 minus 2 minus 26. 0, 48, 10, and 142. 0, 18, 3, and 58. I think I've created my original equation wrong because I can tell from this point that I'm going to get a pivot in every column, and that's not what I wanted. So just give me a moment to fix the problem. Okay. I made a really serious error. I'm going to just call this 3. Nope, just a moment. Okay, this is supposed to be an 11. I did my subtraction, did a subtraction when I should have done an addition. And so I'm just going to redo this. I'm sorry. All right, let's try it again. Make an augmented matrix. Got an X, got a Y, got a Z, got a column for numbers. There's 2 X's, no Y's, and minus 1 Z's. 5, 5 X's, 3 Y's, no Z's is 12, 11 X's, 9 Y's, and 2 Z's is 26. This is going to be even harder to get the 1 in the position where I want it. But I can certainly make a 1. So I could divide by 2 here, and that would be fine, and everything would be in halves, and that would be okay. But it's easier for me to work in whole numbers than it is to work in fractions. I'll make fewer mistakes that way. So it seems to me that if I take off 2 of row 1 off of row 2, I'll get a 1 in that position there, and it might be easier then. So let's do that. my new row 2 will be my old row 2 minus 2 lots of row 1. So this is row 2, 5, 3, 0, 12. This is minus 2 lots of row 1, which is minus 4, 0, 2, minus 10, minus 2 times that, minus 2 times that, minus 2, yep. And so my new row 2 will be 1, 3, 2, 2. 2, 0, negative 1, 5. 1, 3, 2, 2. 11, 9, 2, 26. And then I'll swap row 1 and row 2. One, 3, 2, 2, 0, 2, 0, negative 1, 5, 11, 9, 2, 26. Okay, and let's really hope this one works. So let's make my new row 2 is going to be the old row 2 minus 2 of row 1. That'll put a 0 in this position. So my current row 2 is 2, 0, negative 1, 5. My new, my minus 2 of my row 1 is minus 2, minus 6, minus 4, minus 4. And so I'm going to get my new row 2 is 0, minus 6, minus 5, 1. Okay, and let me do my new row 3 is going to be row 3 minus 11 of row 1. So this is the current row 3, 11, 9, 2, 26. And minus 11 of row 1 is minus 11, minus 33, minus 22, and minus 22. And so my new row 3 is 0. Now 33 minus 9 would be 24. So minus 24, minus 20, minus 4. And so it's become 1, 3, 2, 2, 0, minus 6, minus 5, 1, and 0, minus 24, minus 20, minus 4. Plus 4 here. And I notice that this is 4 times that, and this is 4 times that, and this is 4 times that. And so now, even before I don't need to make a 1, I can do my new row 3 is row 3 minus 4 times row 2. And 24 minus 24 is 4 times minus 6, so I'm going to get a 0. 20 is 4 times 5, I'm going to get a 0. I'm going to get a 0. And it's going to be impossible for me to produce a pivot in this last column, because I'm already going to make a pivot here and a pivot here. There's going to be no pivot in this third column. And I also don't get 0 plus 0 plus 0 equals something not 0. So there will be a solution. So I get a pivot column 2 and 3. Cannot put a pivot in column 2, in column 3. Sorry, pivot in column 1 and 2. Cannot put a pivot in column 3. So since there is not a pivot in every column, it's not a unique solution. We didn't get 0, 0, 0 and something not 0, and so there is a solution. So therefore, we have infinitely many solutions. Now, since none of those planes are the same plane, it's going to be 3 planes meeting in a line. The equations Therefore, the equations define three planes meeting in a line. Okay. So one final example. So you know how back in the first bit I had three lines and I had like a k and I wanted to know what would happen, what values of k made it have, you know, various numbers of solutions? Well, let me do that as well. So consider the system of equations x minus 2y plus 3z equals 1, x plus ky plus 2z equals 2, and minus 2x plus k squared y minus 4z equals 3k minus 4. This is a pretty random and stupid thing to do, but, you know, it does prove definitely that you know how the row operations work if you can do this sort of thing. Okay, so consider, and your answer is I'm considering some fixed constant k. So what we're going to do is we're going to find the values of k that produce that make the solution have the system have no solutions, infinitely many solutions, or unique solution. Which values of k make the system have no solutions, a unique solution, or infinitely many solutions? And, you know, interpret the results. Okay. Now note it hasn't asked me to actually find the solutions for the system. It's just told me what to say how many there are. And I'm going to point something else out. When we say the solutions to a system of equations, we mean the x, y's and the z's. This k is a fixed constant. It's not the same thing as the x, y and z. The x, y and z are unknowns and I'm trying to find all the options for x, y and z. But I'm allowed to choose different values of k and see what the x, y's and z's come out to. So just be careful that they're playing different roles in this system, and so we're not going to treat them the same way. Okay, so we're going to create the equation, the augmented matrix. Okay, we have 1x and minus 2y's and 3z's is 1. We have 1x and ky's and 2z's is 2. We have minus 2x's and k squared y's and minus 4z's is 3k minus 4. Okay, so this goes with the x, this goes with the y, this goes with the z, and this goes with the numbers. All right, my goal is to try and get this as close as possible to having lots of zeros in it. So let's see where we go. So I will make a 0 here and here first. So my new row 1, 2 will be my old row 2 minus row 1. That'll do it. So this is what row 2 used to be, 1k, 2, 2. This is what minus row 1 is, minus 1 plus 2 minus 3 minus 1. And so my new row 2 is 1 minus 1 is 0, k plus 2 is k plus 2, 2 minus 3 is negative 1, 2 minus 1 is 1. And let's do the bottom row as well. My new row 3 is going to be row 3 plus 2 of row 1, because if we add on 2 times 1, we'll get a 0. And then all that plus 2 will have to carry on from everything else. So my current row 3 is minus 2k squared minus 4 and 3k minus 4. And my plus 2 row 1 is 2 minus 4, 6, 2. And so my new row 3 is going to be 0, k squared minus 4, 2, and 3k minus 2, because if we add 2 onto that, we get that. Okay. So my matrix is now 1, minus 2, 3, 1, 1, k, 2, 2, minus 2, k. Oh crap, I'm just copying the original matrix. What am I doing? Row 1 didn't change. Row 2 has become this here. 0, k plus 2, minus 1, 1, 0, k squared minus 4, 2, 3k minus 2. Okay. Well, I don't like it. Well, I suppose the next thing to do, if I'm just telling how many solutions there are, is to try and put a 0 here. Well, I could definitely get rid of the k squared. If I did k of k plus 2, that would give me k squared plus 2k, and then I'd be able to get rid of the k squared, definitely. Yeah. Actually, k squared minus 4 is the same as k plus 4, k plus 2k minus 2. So if we multiply this by k minus 2, we'd be able to subtract that off and get a 0 in that spot. So let's do my new row 3 is my old row 3 minus k minus 2 lots of row 2. So this is what row 3 currently is. 0, k squared minus 4, 2, 3k minus 2. This is what minus k minus 2 lots of row 2 looks like, which is 0. Now k minus, so that'll be minus k squared minus 4. And minus k minus 2 times 2 would be minus I'm just going to give these, I guess it's just minus 2k minus 2. And this will be, no, wait. I'm multiplying row 2, aren't I? So this will just be k minus 2, because they are times by minus 1. And this will be minus k minus 2. So I'm going to get my new row 3 is 0, 0, k, and whatever this works out to be. So where a is 3k minus 2 minus k minus 2, 3k minus 2 minus k plus 2, which is, oh good, 2k. And so therefore we have this matrix Okay. All right. Well, at this stage, I can start to see some things. That bottom row, if k is 0, I'm going to get 0, 0, 0, 0. And there's not going to be a problem with that because that means I'll still have solutions. There'll just be infinitely many because I'm going to prevent there being a pivot in this position here. So if k equals 0, the matrix is 1, minus 2, 3, 1, 0, 2, minus 1, 1, 0, 0, 0, 0. And there is no pivot in column 3, so there's infinitely many solutions. And if k is not 0, then we can do new row 3 is 1 over k times row 3, because I can divide by it if it's not 0, and so I can get 1, negative 2, 3, 1, 0, k plus 2, minus 1, 1, 0, 0, 1, 2. Okay. So if k plus 2 isn't 0, then I've got a pivot in every column. If this isn't 0, I'll be able to divide by it and get a pivot there. So i.e. that k is not minus 2. There is a pivot in every column, so a unique solution. And if k is minus 2, the matrix is now this. And I could add row 3 to row 2. New row 3 is row 3 plus row 2 to get, didn't change, no, not row 3, new row 2 is row 2 plus row 3. Didn't change row 1, 0, 0, 0, 3, and now there's no solutions. So to sum up, if k is 0, there's infinitely many solutions. If k is, what was it, minus 2, there's no solutions. And if k is anything else, there's a unique solution. All right, and that would require us to just only tell how the planes were arranged. So let's see. Wow. Go back to my original equations and let's see if they were parallel. If k is 0, these two are parallel. X minus 2y plus 3z equals 1, x plus 2z equals 2, and minus 2x minus 4z is minus 4. Oh, interesting. They're not parallel. They're the same equation. Oh. So equation 2 and 3 define the same plane. Since everything is the same multiple, this is minus 2 times that, this is minus 2 times that, this is minus 2 times that, they're actually the same equation. They define the same plane, and so we get infinitely many solutions because it's really two planes meeting in a line. Okay. If k equals minus 2, the original equations are x minus 2y plus 3z equals 1, x minus 2y plus 2z equals 2, minus 2x plus k squared y, which would be 4y, minus 4z equals 3 times minus 2 would be minus 6, and minus 6 minus 4 would be minus 10. Okay, so now this equation is minus 2 times x, minus 2 times that, minus 2 times that, minus 2 times that, but this is not minus 2 times that, so the last two equations are parallel. Equation 2 and 3 define parallel planes. So we have 3 planes with 2 parallel. So no points in common. Common to all 3, okay. And if k is not equal to minus 2 or 0, then 3 planes with 1 point common to all 3. You don't have to talk about parallel because that's only possible if none of them are parallel. Okay. So you'll see what happened there. I kept doing row operations until I could get as close as possible to this thing with zeros below, and then I started trying out different values of k. Now, sometimes the quickest way to do this is to say, well, if this position is 0, then either it's going to be a unique solution or no solution. Sorry, if this position is not 0 and this position is not 0, then there'll be a unique solution. And we can say if this position is 0, then it's either going to be infinitely many solutions or no solutions. And if that's 0, then this is 0 as well. So there's another argument for that. It can be a bit tricky to argue these things out. Yeah, but at the very least, when you talk about these things, you have to specify exactly what it is you are looking for to tell you how many solutions there are. And specifically, you want to say whether there's a pivot in every column to get unique solutions, whether there's no pivot in every column to get infinitely many solutions, and in particular, whether you get 0, 0, 0, and then not 0 in order to get no solutions. You have to be very specific about that. Okay, well, thanks for listening.